Our third chapter is all going to be about solving what we call systems of equations, and our first example is going to be solving using what we call some tables and graphs. So basically just visualizing what a system looks like and figuring out our answer from the visual. So if I was to use a graph to solve this system of equations, system meaning two or more equations, that just means if I was to graph this, I could graph each line individually. Where we're going to have an intersection of those two lines, that's where we're going to have a solution of the two, because the intersection where these two graphs would meet, that's where it's going to be true for both graphs at once. So if I want to graph this first line, I could graph that using the x and the y intercepts, using my kind of cover-up method. This is in standard form, so I can tell just by removing the y value, the x-intercept is going to be at 4. And if I was to remove the x from the equation to find the y-intercept, I would just have to take one step and divide by -2, and it looks like we'd also have the y-intercept. So if I put those 1, 2, 3, 4 for the x-intercept, -2 for the y-intercept, if I put those points onto my graph, I could form a line between those, and that's going to allow me to figure out the solutions, of this first one. So if I was to follow that same slope, let's do it on the other side as well. And if I was to graph the second line, the second one is probably easiest just to subtract 3x from both sides. So if I was to subtract 3x, now I have this in our slope-intercept form. So I have an intercept at 1, 2, 3, 4, 5 for my y value. And then if I follow my slope, 1, 2, 3 down over 1, 1, 2, 3 down over 1, it looks like we do have a point where these two graphs would cross. So I'm just going to fill this second line in. And we know that our solution of the system would be at this point where they intersect. So I just want to identify that point. It looks like the coordinates are 2 and -1. And that would be a solution to my system. If I wanted to substitute those points back in, I could also tell it works in each equation. 2 minus 2 times -1. Again, if our y value is -1, that comes out to 4 for the first one. And if I was also to do 3 times 2 minus 1, that's also equal to 5. So I can tell that with that system, again, if I was to substitute 2, -1 into each equation, it would work for both. So now if I'm looking at a second example, this is one for you guys to try. It does work out the same way. I actually saw both of these just using that kind of the standard form method. We can find the x and the y intercepts from the first equation. We get an x-intercept of 2, y-intercept of 4. I can do the same method for that second equation. X-intercept is 2, y-intercept is -2. And as long as I was to find each of those points, again, if I was to find the y-intercept and x-intercept for our first line, and our y-intercept and our x-intercept for the second line, it actually looks like these two meet on one of our x-intercepts, which is just at 2, 0. And again, if I wanted to substitute into my equation, 2, 0 should work in the first equation, 2, 0 should work in the second equation, so I know I have a system, I have a solution to my system, because it does work in both of those two equations. So I can also use this with word problems. Only difference is now we have to make the system ourselves, so we have to come up with a couple equations. And if I want to identify variables first from our word problem, in this question we're buying a total of 6 pens and pencils, so we want to think buying the pens and buying the pencils, and also just looking back down to the end of the problem, the number of pens, the number of pencils is going to be what we're trying to answer for. So let's identify again x, we can just call as the number of pens, and y we'll call it as the number of pencils. Could be, any variable we choose, but we'll choose x and y to keep that simple. And now if I want to make a system, we have two pieces of information basically, which is how many pens and pencils I'm buying, and also how much I'm spending on those. So if I want to make an equation out of the first situation, if I know it's a total of 6, I know that no matter how many I have of each, pens and pencils, they are going to add up to 6 all put together. And if I want to figure out an equation for the cost, if I know that pens cost $1, that's like saying $1 for every pen. You could also just put x by itself, and 50 cents for every pencil. So let's say like 0.5 for every pencil. That's going to make $4 for my equation. So now that I want to graph this, I want to approach this just like our last situation. Again, it's pretty easy to get this from the intercepts because it's in standard form. X-intercept is 6, y-intercept is also 6 for my first equation. You can also get something like a slope from there too. So let's say if I want to get other points, we know it's just going to follow that like down 1 over 1 kind of pattern. And if I want to figure out the line between those, it's just going to fit between those two intercepts. That's going to be my first line, and I want to see where the second one meets. So same thing, I think I can solve this using our intercepts method. We know that the x-intercept would just be 4, and if I want to find the y-intercept, it looks like we just have to multiply both sides by 2, or you can think divide by a half, same thing. Either way, we're going to get a y value of 8 for that next intercept. So if I have a y value of 8 and I have an x value of 4, it also helps again if you're thinking of like simplifying a slope. Let's say if you want more points to be more accurate, if I go down 8 over 4, that can be simplified to down 2 over 1. So that can also help fill out some other points along the way. and it looks like we already do have a match. So if I do connect those and form my line, should I extend that line a little bit, I guess. Go there. It looks like we do have an intercept already, or sorry, not an intercept, an intersection, and that would be at this coordinate right here where it looks like those two cross over. So I just want to identify that coordinate. It looks like the x value is 2, y value is 4. So at that point 2, 4, that would be the solution on my graph. But now that this is a word problem, we want to make sure we can actually answer this back in terms of our variables that we identified. So if the x value is 2 and we identified that as pens, we know that 2 pens would be what we can afford. And if I know the y value is 4, that's going to be 4 pencils. We know that if 2, 4 is a solution, I just want to put that back in terms of my two variables. So looking at that second example, again, I kind of highlighted the variables already in this first part. So I said that cheese pizza in this case was x, pepperoni was y. I guess using that hint, maybe you can set up a couple equations there and solve it just like that last one. But looking at our answer now, looks like that's going to be, again, one equation describing how many pieces you have. If I have 7 slices put together, that's just cheese and pepperoni added together to get 7. It's a little bit awkward when you use the price equation here, because if I have $1 for every cheese slice and $1.50 for every pepperoni slice, no matter how you slice it, I guess is a pizza joke, we're going to have some kind of a fraction for our intercept. So you do want to be a little bit careful how you're graphing this one. I tried to graph these as close as I could and double check to make sure that 5, 2 was our solution where they was crossed over. If I was to plug those back into my first equation, again, 5 for x and 2 for y, it does work in terms of number of slices. Add them together, we get 7. And if I want to plug those back into my cost equation, again, just verifying that that was our correct intersection point, that works in our cost equation as well. So it's always a good idea if you think something's a solution on your graph, just make sure your graph's not a little bit wonky and you don't have your lines meeting at some other place. Plug that back into your system and that should work for both equations. If it does, you're going to have that solution. So last thing we're talking about here is inconsistent and consistent, independent, dependent, this sort of thing. So essentially it just means what we've seen before with some situations where if I have lines that cross over, they're just going to have one intersection, and that's going to be the one solution that we found previously. If I have what we call coinciding lines, so that's going to be basically lines that lie right on top of each other. Say if I was graphing the first line and the second line fits right over it, that would be what we call infinitely many solutions, because any point on those lines is an intersection. Or I could also be dealing with a third situation where the lines are parallel, and since they have no intersection, they're not going to cross over each other, there would be no solution, and we would just call that an inconsistent system. So it's just going to be 3 terms we have to remember. Independent if they cross each other at one spot, dependent if they're graphing the same line twice, so infinitely many solutions, and then inconsistent if they're parallel and they don't actually have any solutions because there's no point of intersection. So if I want to tell if it's either situation here, again, we're just going to do one problem and see if we can figure out the same kind of pattern on the rest. I'm going to do the first one in red and the second one in blue as I did in the other examples, just to kind of keep these together. But yeah, if we want to tell if it's independent, dependent, or inconsistent, essentially all we have to think of is, would these lines intersect? Would they be the exact same line, or would they just be parallel? So as long as they have different slopes, that's going to be one solution, as we've seen in our last few examples. But if they have the same slope, again, I could either have the same line and have them be dependent, or I could have them be parallel and they're going to have same slope at different y-intercepts. So if I want to try that first one, again, if I was to put these all into slope-intercept form, that's why y equals mx plus b. In the first one, all I got to do is add 3x to both sides, and that's already the y isolated, so I just get y equals 3x plus 4. We can tell the slope is 3 and the y-intercept is 4. If I try to do the same thing on the next one, I would have to take a couple steps, so subtracting x to start, I get negative 1/3 y equals negative x plus 1. And then if I was to multiply by negative 3, again, we want to isolate for that y value. Multiplying by negative 3, now I get a 3x, and again, notice that first equation, we have our slopes matching. And it looks like multiplying by negative 3 for my y value, or sorry, for my constant term, I get 3x minus 3. But if I have those two graphs, again, 3x plus 4 and 3x minus 3, if they have the same slope but the different y-intercept, it's going to look like these kinds of parallel lines in our system. So we know if they're parallel lines, this is what I call an inconsistent solution. Sorry, I ran a space on that box there. Hope you can read that that's inconsistent. But yeah, if it's inconsistent, again, that's just because they would never cross. If I have the same slope, I'm not going to be intersecting. And also if I have different y-intercepts, that means we're not just graphing the same line twice. Trying those other examples, again, basically the same thing. We want to get into y equals mx plus b form. and then try to identify would they have a point of intersection. In our second example, if I graph both lines, it looks like the first one has a slope of negative 2/3, intercept of 1/3. Second one has a slope of negative 4. So as soon as they have different slopes, I know they're just going to intersect at one point. So that would be one point of intersection. That's going to be an independent solution. If I was to try the next one, again, just by getting that into y equals mx plus b, first one takes it easy on us because the first equation is already in slope-intercept form. And then with the second one, since I can translate and get that into that same form, if I get the same exact equation twice, 2x minus 3, 2x minus 3, it means I do have the same slope and the same intercept. I'm essentially graphing the same line twice, so that would be a dependent solution. If I was to try those last couple, same idea on that got it question. We just want to see again what this looks like in slope-intercept form first. I get on the first line a slope of 3/2, an intercept of negative 5/2. And then if I have a negative, again, these would be perpendicular lines. So if I change the signs on this one, we do want to be careful of when I'm solving this and I get different sorts of signs. But yeah, if I change the signs, that's going to mean that they still are perpendicular, and that's going to mean one point of intersection. One point of intersection makes that an independent system. So if I was to answer these last couple conceptual questions, is it possible to be both independent and inconsistent? Well, let's go back and see. If it's independent, that would be one solution. If it's inconsistent, that's no solution, so they wouldn't be crossing at all. And we know there's no case where lines can be both parallel and intersecting, so that's my answer here. If they can't be parallel and intersecting, there is not going to be a system that's going to be independent and inconsistent. So if I also wanted to write a linear equation system that had no solution, again, all we're thinking is they just want to be parallel. That means if I was to write a system myself, I just want to make sure of two things. They need to have the same slope. They need to have different y-intercepts. That makes sure I have parallel lines, which are never going to cross, but they're also not graphing the same line twice. So that's going to be our inconsistent system that has no solution.